Okay, so let's start. Uh, Let me remind you what we were doing. Last time we started studying limit superior and limit inferior. Let me quickly remind you what we have done. We take any sequence. If it is bounded from above, then we define the following sequence, Bn. Bn is defined as the supremum of all the terms of the sequence with index larger than n or equal to n. So B1 is the supremum of all the elements. B2 is the supremum of all the elements whose index is at least 2. B3 is the supremum of the set of all elements with index at least 3, and so on. Since this set is contained in this one and this one is contained in this one, so this is a nested sequence of sets. Therefore, supremums form a decreasing sequence because each time you take the supremum of a smaller set. Conversely, if you assume the sequence is bounded from below, then you can analogously define the infimum sequence as this time infimum of the same sets we considered above. Since again, okay, let me maybe write a couple terms. So what is C1? C1 is the infimum of A1, A2, A3, and so on. C2 is the infimum of A2, A3, and so on. And C3 is the infimum of A3 and on. Again, these are nested, but this time you take infimum. Of course, the smaller the infimum of a smaller set will be bigger probably. So this is an increasing sequence. Okay, increasing sequence. Let me do a couple examples, to understand what's going on. For example, let's say AN is this sequence. Let's say 0, 1, 0, 1 over 2, 0, 1 over 3, 0, 1 over 4, and goes like this. So 0, 1 over n. Let's consider what are bn's and cn's. What is, for example, b1? It is the supremum of, right, all these sets, all these elements. So what are these? I take 0, 1. I don't take 0 anymore because it's already there. 1 over 2, 1 over 3, and so on. So what is the supremum? Well, supremum is clearly 1. What about B2? It is the supremum of 1, 1 over 2, 1 over 3, and so on. It is still 1. B3 will be supremum of 1, 1 over, no, sorry. I'll start from 1 over 2, 1 over 3, and so on. So it is 1 over 2. And you see how it is, how it will go, right? So this will be supremum of what? Nth element. Well, actually, here I should also have 0, right? Because I start from the second element, so it's B1 and then 0. So 0 is here also. 0 will be in each of them, 0. So it will be, okay, maybe I should do like this. What is B4? 1 over 2 and then uh, 1 over 3 and so on. So it is again 1 over 2. B5 will be 1 over 3 and so on, right? So the sequence Bn is something like this. 1, 1, 1 over 2, 1 over 2, and then I guess we will have 1 over 3, 1 over 3, and so it will go like this, okay? What about Cn? C1 will be infimum of this set 0, 1, sorry, 1 over 2, 1 over 3, and so on. So the infimum is 0. What about C2? It will be the infimum of, I will start from the second element. It is 1, but then there is 0 also, and then 1 over 2, and then there is 0. I don't write it. So like this. Infimum is still 0. C3 is infimum of, I'll start from the third element. It was 1 over 2, or no, third element 0. So again 0, and then I will have 1 over fourth element is 1 over 2, 1 over 3, and so on. So it is again 0. I take infimum. Infimum always will be 0 because 0 repeats infinitely many times in this sequence. So 0 will be in each of these sets. So Cn is just 0 for all n. Okay, for all n. So Cn is the 0 sequence and Bn is this sequence. And finally, note that, both limits. This is a decreasing sequence and bounded from below by 0. This is an increasing sequence. Actually, in this case, it is just a constant sequence and it is just 0. And they have both limits. The limit of this one is 0 and the limit of this one is also 0. Okay. Do you have any question about this? Another example. Let's say evet. B4 dördüncü elemandan başlayacağım. 1, 2, 3, 4. 1 bölü 2'den başlıyorum. Yani şöyle aslında demem. Yani fark etmez tabii. Küme 1 bölü 2 var. Sonra 0 var. Sonra 1 bölü 3 var. 0 var. 1 bölü 4 var. 0 var. Süpremumu bunun 1 bölü 2. Değil mi? Hı hı. Bir başka örnek yapalım. Mesela AN şu olsun. 1 eksi 1 evet 1 bölü 2 eksi 1 bölü 2 2 bölü 3 eksi 2 bölü 3 3 bölü 4 eksi 3 bölü 4 bu şekilde gitsin. Yani n bölü n artı 1 var. Sonra eksi n bölü n artı 1 var. Ve bu şekilde gidiyor. Şimdi B1, what is B1? B1 is the supremum of all of these, right? Supremum of all of these. What is the supremum? Well, it is 1, right? Because these are all less than 1, and 1 is already here. So supremum of 1 minus 1, 1 over 2, minus 1 over 2. So like this, it is 1. What is B2? It is the supremum of minus 1, 1 over 2, minus 1 over 2, 2 over 3, and so on. supremum of all these elements? Well, you see, I have n over n over n plus 1. As n gets larger and larger, this gets closer and closer to 1. Therefore, supremum will be 1. B3 will be supremum of 1 over 2 minus 1 over 2, 2 over 3 minus 2 over 3, and so on. Supremum is again 1. And you see that Bn is just the constant. So Bn is the constant sequence 1, 1, 1, 1. And similarly, Cn, so infimum of, you know, an plus 1, and so on. When you take infimum, this time you will get, each time you see, infimum of this will be minus 1, minus 1, again minus 1, because this time I have minus n over n plus 1, and the infimum is just minus 1. So this time it will be minus 1, okay, for all n. So both sequences are constant sequences, right? Bn is the constant sequence 1. Cn is the constant sequence. Maybe I should write like this: 1, 1, 1, right? Cn is this sequence: minus 1, minus 1, minus 1. They are both constant sequences. This time limit of Bn is 1 and limit of Cn is minus 1. These limits have names, right? So let me write as a definition. If the limits exist, and maybe before the definition, when these limits will exist, well, if the sequences Bn is bounded, if Bn is bounded, I mean bounded from above and below, then, not Bn, I am sorry, Cn is bound, not Cn, An is bounded, then Bn is a decreasing sequence, bounded from below, because all the terms of An are bounded. They are less than some number and greater than some other number, so they are inside between two numbers. So everything is bounded, but this is a monotone sequence which is bounded, and thus it is convergent. Similarly, Cn will be convergent, provided that An is bounded, of course. Yes. Decreasing dediğim şey şu: her bir terimi bir öncekinden küçük veya eşit. Yani sabit bir dizi hem decreasing hem increasing. İlla böyle strictly decreasing kısmı olur olması gerekmiyor. Ve elimizde şöyle bir şey var. Dikkat edin. Yani say an is less than, greater than little m and greater than less than big M for all n. Okay. So bounded means this, right? Maybe I should write for some m and m, and for all n. Okay. Then I have this. B1 was uh, this was a decreasing sequence. It is less greater than B2, B3, and these are all less than M, of course, because supremum of ANs, any subset of ANs is less than this. And I know that of course Bn is always larger than Cn, because this is the supremum of a set and this is the infimum of the same set. So Bn is always larger than Cn. And I have this. So here I have Cn. This time they are increasing. uh, Cn plus 1 and goes like this, and this is larger than little m, because all the elements are larger than m, little m. So Cn is an increasing sequence and Bn is a decreasing sequence. Okay, one of them is increasing, one of them is decreasing, and uh, and always Cn is larger than Bn. Okay. Efendim? Evet, Cn azalan artan bir dizi ya. Ha, pardon, artan dizi. Şöyle, şuraya, özür dilerim. Haklısın. Şöyle demem lazım. Cn artan bir dizi. Ha, şöyle demem lazım. Özür dilerim. C1, C2, C3, right, like this. Cn. Tamam. Cn is increasing, Bn is decreasing, and they are getting closer to each other, and they are both limits exist, right? The limit of this sequence, so limit Bn, of course, exists because it is decreasing and bounded from below. So this limit and okay is called, I already said it is the limit exists, is called lim sup an, and limit Cn is called lim inf Bn. Okay, so they have names like this, and again, of course, clearly lim sup an is larger than or equal to lim inf an. They are both an, because this terms of this sequence are always larger than the terms of this sequence. Therefore, if the limits exist, and they exist in this case, the limit of this one will be larger than or equal to the limit of this one. The question is, when these two limits exist, I mean equal, you see, if we go back to our examples, this was an. What was liminf in this case? So liminf, limsup, sorry, limsup an. So limit of bn's was 0, right? This is 0, and limsup Liminf an, it was the constant sequence, and it was again 0, so the limits equal and both 0. And if you notice that actually in this case our sequence is convergent to 0, so to the same limit, right? What about this one? Here lim sup, they are both constant sequence. Lim sup was so lim sup an is 1, and lim inf an, it is the constant sequence -1, right? -1. So it is -1, and they are not equal. They are not equal. And in this case, our sequence is not convergent either, right? It has a subsequence converging to 1, and it has a subsequence converging to -1. And if it were convergent, then we know that all the subsequences would converge to the same limit, right? The limit of the sequence an. So there is a relation between all these limits, and here is the actually observation. Let me write as a proposition. So assume an is a bounded sequence. Then lim sup an and lim inf an, they both exist. Moreover, this limits equal lim sup an is equal to lim inf an if and only if limit an exists. So if this limit exists, then both limsup and liminf exist, and they are equal to each other. And if they are equal, then limit an exists. Okay, which confirms our examples. Maybe I may talk about this proof. Do you have any questions so far? Okay. All right. So let's prove, for example, this direction first. First, assume that so we already assume it is bounded. We assume that okay, lim sup an is equal to lim inf an. So what are we going to prove? We must prove limit an exists and equals limsup. Maybe I should write here also exists and equals this common value lim sup an, which is equal to lim inf an. You may also think of this proposition as a characterization of convergent sequence, right? For a sequence to be convergent, Limsup and Liminf should exist, and they must be equal to each other. Okay, now why this is the case? Well, let L be this common Limsup an, which is also Liminf an. Okay. Uh, okay, we of course have the following, right? An, sorry, what was Bn? Bn was the supremum of, right, an plus 1, and so on. So this supremum is of course larger than this, and uh, this is clearly larger than or equal to infimum of these elements, and this is just Cn. So An is sequenced by Bn and Cn, right? I have this Bn, An, and Cn for all n, and I know that this sequence and this sequence has the same limit. Well, this is by the sequencing theorem, right? By the sequencing theorem, then by the sequencing theorem, uh, sequencing lemma, maybe. Uh, maybe I should just prove this because we haven't proved, I guess, this result, right? You have seen maybe this in the first year calculus course, but we haven't proved this. So claim whenever you have this, uh, okay, assume, let me prove this as a separate, we have three sequences. We have three sequences, an, bn, cn, with this an, sorry, bn is greater than an, greater than cn for all n, and limit bn is equal to limit cn equals l. Then of course limit an exists and equals l. Why is that? Well, proof is very simple. Let epsilon be given, right? Uh, both sequences are convergent, right? Then since limit bn is equal to l, there is some n1, let's say, with n greater than n1. We have what? N greater than n1 implies what? Bn minus l is less than epsilon. Similarly, there is n2 because Cn is convergent, so that n greater than n2 implies Cn minus L is less than epsilon. So we have, maybe I should make this epsilon over 2, okay, epsilon over 2. Then we have the following. So if n is greater than n0, which is the maximum of n1 and n2, then I have the following. N will be larger than n1, therefore we will have Bn, which is greater than L minus epsilon over 2, right? Epsilon over 2. But Bn is less than An, no. Was larger, right? So I should write this the other way around. Epsilon over 2 and C, okay, An is larger than Cn, and Cn is larger than L minus epsilon over 2. Well, maybe I don't need epsilon over 2's, right? Epsilon would be fine. I thought, okay, yeah, I don't need epsilon over 2's. We have this. So this means if n is larger than, no, I already said this. So An is less than L plus epsilon and greater than L minus epsilon, and An is between Bn and Cn. Thus, An minus L is less than epsilon if n greater than n0, and this means hence limit of An is equal to L. Okay, and this finishes the proof. So this proves one direction. Okay. For the other direction, so this time you do what? You assume, this time assume that limit An exists. Say limit An is equal to L. What are we going to prove? We must show uh, both limits An and Bn should exist. So limit Bn, so Limsup An and Limsup Bn should exist. Okay, maybe I should write Limsup An, which is limit Bn, should be equal to limit Cn, which is Liminf An. So we must prove this. Let me give you the idea, but I will not write down the proof. I will leave it as an exercise. So I will leave this as an exercise. But you know, idea is simple. You see, sorry. Here is L. I want to show that these limits exist. So you say choose some epsilon. I have L plus epsilon, L minus epsilon. I know that there is some index, right? There is some index n0 such that n greater than n0, all the terms of the sequence are inside this interval. So an0 is somewhere here. an0 plus 1 is here. an0 plus 2 will be here. So all the terms of the sequence after this index will be here. In particular, what you will see, what about, for example, Bn? Bn is the supremum of all these, but these are already between L minus epsilon and L plus epsilon. So the supremum, maybe I should say uh, Bn0, right? Bn0 will be will be in this interval. So it will be, and if I choose maybe this epsilon over 2, so this will be certainly L minus epsilon and L plus epsilon. I cannot write epsilon over 2 because supremum might be equal endpoint, okay, and infimum might be equal to the endpoint. But if I choose this epsilon over 2, then Bn0 will be like this, and Cn0 again will be like this. All right, and we know this Bn0 is always larger than Cn0, right? And Bn0 is a decreasing sequence, and this is an increasing sequence. So this Bn0 is somewhere here, Cn0 is somewhere here. This is increasing and this is decreasing, and they are both getting closer and closer to L. So I will leave the rest to you, okay, as an example, I mean as an exercise, uh, uh, so that you will show that both limit of Bn and Cn are all equal to Cn0. Okay. All right, let me okay, so we uh, finished the first part of the first chapter of the book. Let's start with the second chapter. So chapter 2. Metric spaces. As I said earlier, metric spaces will be a generalization of real number system, and so we will consider general sets, not the real numbers, as set, and the metric will be a generalization of the absolute value. Remember that absolute value gives us the distance between two real numbers, right? Absolute value of a minus b is the distance from a to b. And a metric will be just, an analogous, function replacing the absolute value function on real numbers. So let me just start with the definition. You have seen actually many examples of metric spaces so far. We just didn't call them a metric space. Okay, a metric or a distance function, right? So metric is a function which measures distances on a set X, is a real valued function D from x cross x into R, which satisfies the following properties. What are these? We will call these properties M1, M2, M3. M stands for the metric. So the first property is this. Since this is the distance between 2 points, it will denote the distance between 2 points. Distance is never negative, right? So this is always non-negative for all xy in x, and this distance equals 0 if and only if x equals 0, right? If the distance between 2 points on a set is 0, then they should be the same point. So this is our hypothesis for a function to be a metric, okay? It should satisfy this rule. If dxy is 0, then x must be equal to y. Otherwise, I cannot call D a metric. The second property, or the hypothesis D should satisfy, it should be symmetric, right? Distance from x to y should be the same as the distance from y to x. So dxy must be equal dyx for all xy in x. Okay, this is the symmetry property of a metric. And the third one is maybe the most important one. Well, they are all important. The triangle inequality. Distance from x to y should be less than distance from x to z plus z to y for all x, y, z. Okay, this is called so M3 is called it's called the triangle inequality. Why? It's very simple. So this is the not what I'm going to draw is not a real picture. It is just a picture, symbolic picture. So we have let's say the point x, point y, and point z. And what does this tells us is the following: distance from x to y is less than the distance from x to z plus the distance from y to z. This will be the real picture when I consider R2 as my metric space and D2 is the usual metric between these 2 points. But in general, I cannot draw you the picture of X because I don't know what is X, right? X is just any set, and I don't know, how to represent the distances between those points. In the plane, I can just draw some lines and so on, but this is just a symbolic picture. However, this symbolic picture is a very, good uh, way of seeing what's going uh, on the real picture. Actually, we will always deal with, draw symbolic pictures like this, but we will see that they are very helpful, and actually they uh, give us idea about what's really going on. So although it is, symbolic, it will be very important. And this tells us that, this distance in a triangle, the side length for one side, the length of one side is always less than the length of the remaining two sides, right? Yani bir üçgende her kenarın uzunluğu diğer iki kenarın uzunlukları toplamından küçük veya eşittir. Okay. So this is the triangle inequality. So what's a metric space? Metric space is a set. I didn't tell you what's a metric space. I told you what's a metric, but I didn't tell you what's a metric space. So another definition. If D is a metric on a set X, then the pair XD will be called a metric space. Okay, a metric space. Before I give some examples, I will give you some immediate properties one can obtain from the hypothesis. So let me just write it down. Proposition. So this is the generalized triangle inequality for any x1, x2, xn in a metric space. Metric space xd, we have the following. This from x1 to xn is less than distance from x1 to x2, distance from x2 to x3, and so on up to n minus 1 n. Okay. How can you prove this? We can prove this using induction, right? Induction on n. Okay. Let me do this after the break. Let me stop at this moment. In the second hour, I'll prove this.